Okay, how are you? Hope everybody's doing well. We have one more person joining us and maybe another person or two as the class goes on. Second exam is behind us. Third exam is in front of us. It's the week after next. That ends this semester for us. Remember, there is no final exam in this class. There is just the last of our exams. So the content that we're doing from this point forward is a lot less mathematical. You can make it mathematical if you want. There's no harm in that, but it just happens to be that there's a lot less math that's involved with the work that we're going to be doing from this point forward. It's much more conceptual, which might play to the strengths of some and the weaknesses of others. Who knows? But what we're going through today is the 8th chapter of TRO. One of the more interesting areas in all of chemistry that we end up teaching, just because it happened not that long ago. So it's all in recent memory, and we're interacting with it more than we ever really have in my lifetime and in all of yours as well, I'm sure. So I'm going to get right to it. And there'll be a couple times when I sort of like pause and break and share, like right now, because there's a kid coming to the door. So excuse me 1 second. He is, but I'm just watching. So I'll send him out later. All right, sorry about that. Okay, this is not my office where I'm doing this. Is from the right close to the front door. All right, so I'm going to start sharing my screen. That. All right, so just some important stuff. We're going to be going through the electromagnetic spectrum, the relationships that make up the electromagnetic spectrum. We'll talk about what the photoelectric effect is without really doing any math on it. And then we'll get into models of the atom, Bohr model, and the quantum model. So the important dates that you want to keep in mind is that this Thursday we'll have our next quiz. On Friday, your extra credit is due, and then on Sunday, your homework is due. So we're going to have another round of both extra credit and homework for next week. Okay. All right. But we should get through all of this chapter today so that we can go on to chapter 9, which is very complementary to this chapter. So it all sort of makes sense. Good. So electromagnetic radiation, right? This is the stuff that you guys have been awash in ever since you were brought on this earth. And basically it's light energy. It's different regions of light energy. And the light energy that we can see is this little bit right here in the middle, this visible spectrum. Okay, there's a whole lot of light we interact with that we can't see. Radio waves are probably the most important to us in terms of communication, but everything else, it's all there. It's just that our eyes were never built to see it. So we miss out on all of this stuff. These numbers down here refer to a wavelength, and we're going to get to what that is in a second. So wavelength and frequency are things that we associate with waves. And right now, the way we're going to treat light or light energy is as a wave. That will not be the only way that we treat light as we move on to this chapter. So one of the things we can quantify about a light wave is its wavelength. And so if I'm sort of like going in this sinusoidal pattern here, a wavelength is the distance between any 2 points that have the same amplitude. We typically say peak to peak. We can also say trough to trough, so long as the amplitude is the same. So this point over to this point here, that would be all equal measures of the wavelength. It just so happens that with the math that we can do, we can take derivatives of this and then watch how that changes as these things move around. It's just much easier to do from peak to peak. So red would have a relatively long wavelength. Yellow has a shorter wavelength, and this is like a green-blue. This has an even shorter wavelength than that. The brightness of something has to do with what's called its amplitude. And so if you imagine this straight line right here in the center, the amplitude of a wave is how much it's disturbed from that center line. So above and below, going a great distance, that is a large amplitude, which for light we interpret as how bright that is, or how dim it is with a much smaller amplitude. Wavelength, as a unit of distance, gets its own symbol. It's this little Greek letter here called lambda. And frequency is the other one we look at. So if you can imagine this red dot right here is watching this wave go past. The number of times a wavefront goes past it per second is called its frequency. That gets measured in a unit called hertz, which has a few different ways of being represented. Hz is one representation of it. Seconds to the -1 is cycles per second, which is another way of saying reciprocal seconds, or 1 over s. It also gets a symbol that looks sort of like a fancy V, or nu. A lot of our physics textbooks end up showing frequency abbreviated with an F. That's fine too. Different groups will do it in different ways. All fine, so long as we understand that it's the number of times a wave cycles per second. And then the speed. How fast is that wave going? Well, that's going to depend a little bit on the medium. Sound waves travel at 343 meters per second. The speed of light, however, is the speed we're interested in. And the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. Okay, so it's incredibly fast. It is still a speed, which means that if we're traveling some distance, it takes some amount of time to get there. So the light that we get from the sun, 93 million miles away, traveling at this speed, nearly the speed of light, takes between 7 and 8 minutes to get to us. So if our sun were to explode all of a sudden, we wouldn't know for 7 to 8 minutes. And then we'd find out in a big way. But this is the speed, okay? And it becomes an important number when we're further and further distance between two things. So if we're trying to communicate with Jupiter, there can be a pretty significant lag between us and them because there's a really big distance. And even at this speed, it takes some time. So there are some equations that we can use, and we'll use that to solve a problem that looks like this. So lambda times nu equals c. That is the first of our equations. And lambda is the wavelength, so it's a unit of distance measured in meters. Frequency is measured in 1 over seconds, and so the product of those two things is a speed, meters per second. So that's where lambda times nu equals c ends up coming from. So because we're talking about light waves, this c is a constant, 3.0 times 10 to the 8th meters per second. If we were doing this in other media and other kinds of waves, we would use a different number for this, but this is the speed of light that we're using. So generally speaking, if I know the speed of light and the wavelength, I can get the frequency. Or if I know the speed of light and the frequency, I can get the wavelength. Okay, it's knowing one thing and solving for the others. And so that's the equation I would use with this. I'm asked about the frequency for a wavelength of light that is 252 nanometers long. So I just sort of plug in for the things I know and don't know. So 252 times 10 to the minus 9 meters is my wavelength. Now notice I did not do 2.52 times 10 to the minus 9. I just changed nano into what it means, 10 to the minus 9. So this would actually be, if I was doing it in true scientific notation, 2.52 times 10 to the minus 7. Won't make a difference here. Times the frequency equals the speed of light. And just speed of light divided by the wavelength will give you the frequency, which comes out to be 1.19 times 10 to the 15 per second. That number should make sense as a large number, meaning that 252 nanometer light in the ultraviolet is going to cycle really fast. So with that information, what we're going to do is we're going to walk down the electromagnetic spectrum. We're going to start at X-rays and go all the way down to radio waves. And one thing I'd like to point out is that every time my wavelength gets smaller, this ends up changing as well. So if this gets larger, this ends up getting smaller. They're inversely proportional. So this is just like Boyle's law, pressure times volume equals a constant. If pressure goes up, volume goes down. Same thing with frequency and wavelength. As wavelength goes up, frequency goes down. As frequency goes up, wavelength goes down, because the product of them has to be a constant speed of light. So we use X-rays in all sorts of things, usually for finding out what's going on with our bones. They're usually telltale things that are going on. If you end up having any metal in you for whatever reason, a new knee, a hip replacement, anything like that, metal scatters this light. So what you're seeing here, the white images, are these scattered parts of X-rays. So X-rays end up coming from some high energy source. They spit out at you. You don't want to be overexposed to X-rays, but you want the right exposure. And at least for a long time, we've been doing this on film. Now we're doing it all electronically. But on film, the white parts here are where the X-rays scattered, and then the gray parts here are where we end up seeing, X-rays going through. So bones scatter it pretty well. Metal scatters it very well, exceedingly well. So, we end up using them in X-ray and dentistry and all sorts of fun stuff like that. But we can also use it in what's known as X-ray fluorescence, XRF. And this is a non-destructive elemental analysis. And so you can get this thing that looks like a pricing gun, right? If you ever have to work in a store and you're using a pricing gun, this is about the size of a pricing gun. It's considerably more expensive than that, though. So you have some small X-ray source that'll shoot X-rays out at a surface, and then something will bounce back, some energy, and then that energy can be processed and give you a sense of what you're looking at. And it's actually a really powerful tool because it can fit, in your hand. And so this is what something like that might look like. You've got some digital display, and I am highlighting, I don't know, like a piece of gold or something, and I can see that this piece of gold is 18% silver, 75% gold, and almost 7% copper. So we're getting some good information here. But every element will interact with X-rays differently, which means that it can be a really good analytical tool. We can use it to tell two different metals apart because a lot of metals might end up looking exactly the same. So this allows us to help tell them apart. Ultraviolet light, we're here where the wavelength is 100 times larger, so 10 to the minus 8 instead of 10 to the minus 10. And when I say 10 to the minus 8, that is not a single wavelength. That represents a range of wavelengths that include 10 to the minus 10. So the energy of these ends up being 2 times 10 to the minus 17 joules. We'll get into how that's calculated later. And then the frequency is 3 times 10 to the 16. So as this number ends up getting larger, this number ends up getting smaller. And this can drive chemical reactions, and it's dangerous to tissues. It's one of these things that we watch out with respect to cancer. This is what's called a UV-vis spectrophotometer. We have one of these in our lab, and this is what it spits out. So in a little cuvette, I would put a molecule in there, and then wavelength by wavelength, we'd shine light on that, and some of those wavelengths would be absorbed a lot, and some of them would be absorbed a little, and this peak would tell me something I want to know. This is NAD oxidized, and one of the things that happens here is you can see there are a lot of double bonds in this molecule. We haven't learned much about double bonds or how they work, but having a lot of double bonds in a molecule increases the amount of light that it ends up absorbing, especially in the ultraviolet. Which brings us to visible light. So visible light goes from roughly 400 nanometers to roughly 800 nanometers. That's a pretty good range for the things that we can see. So its energy is on the order of 10 to the minus 19th, and its frequency is on the order of 10 to the 14th, and it's got a very weak interaction with matter. So if you're shining visible light, like a flashlight on matter, not much is going to happen. There are some chemical reactions that can be driven by this, sure, but for the most part, not much happens. Usually it just ends up getting scattered, and we're able to see those colors. One thing I want to point out is that the violet portion of this rainbow, this Roy G. Biv, the violet portion is here at about 400 nanometers. And the red portion is here closer to 800 nanometers. So the red portion of this has a longer wavelength than the purple portion. So that means that if this has a longer wavelength, this means it has a smaller frequency. And if this has a shorter wavelength, this means it has a larger frequency. So the higher frequency light is here by the ultraviolet, and the lower frequency light is here by the infrared. One of the things we're going to find out is that frequency and energy are directly proportional. So this is the energetic side of things, and this is not the energetic side of things. Okay, so when the weather people on TV are telling us that things are going to get hot, they show us this color red, and red means cool, actually. Okay, not in weather, but it means cool in terms of the spectrum. And when they show us something that's going to be cool or cold, they show us blue, and that is also not correct because this is much more energetic. This should be the hot portion of the spectrum. But the place you guys interact with this is on all these wonderful, cool displays that we have, right? These cell phones that give us all these wonderful, pretty pictures right here, okay? So one of the reasons that we can do that is because we've got these light-emitting diodes. So these were a wonderful invention when they were introduced, I think, in the 1950s. We didn't have a lot of understanding of their use then, and we've come a long way since then. Getting a message here that says my internet connection is unstable. If I start to break up, please hit me in the chat so that I can make a correction. But that's the only way I'll really know unless you unmute yourself. So these LEDs right here, these emit wavelengths of light, and then this colored glass around it, they sort of like, you know, will filter out light so it appears a certain color. And this is like a very large version of this. The very small version of this is what's called organic LEDs or OLEDs. And if you're an organic chemist, chances are you might be working on something that's important to this industry. So in the way that all these OLEDs work is there's some kind of substrate, you know, glass in most cases. Your phones are typically have a glass substrate. And then there's an anode where electrons kind of come in and they go to a cathode and then they go back around so they complete a circuit. And they're going to go through some conductive layer so they get to spread out, and then they go through some emissive layer, which is when electrons go through this, they make this give off light. And in doing so, you know, we can start to see images. So these OLEDs are cool because you can basically apply them like a paint. All of these things can be made smaller and you can apply them in broad strokes. What does that mean? Well, at some of the consumer electronics shows, you are seeing impressive looking televisions, pictures and whatnot that are getting impressively small. Like this one is basically wallpaper, the thickness of something like that. These are new kinds of lights that we're starting to see around because all we really need is the RGB in order to make white light. And because we can make blue LEDs, it's relatively easy to do. So we can tune that light. And so now we're starting to see white light sources that don't have to look like their traditional like Thomas Edison type light bulb. They can look really like anything. And so people are taking advantage of that. We're seeing neat lighting. Flexible screens, that is one of the new really exciting things people are working on. We can get screens around curved surfaces. We can get them onto watches, rings, bands, and things like that. So this is, you know, one example with obviously an Apple kind of thing going on here. For whatever reason, the flip phone just sort of needs to come back. So foldable versions of these kinds of phones are something we can probably expect in the not too distant future. Now, the next one I'm going to get you to is interesting. So here is a fart. Gotta have it. So this is infrared radiation. Infrared radiation is basically heat. And so when molecules interact with this kind of radiation, they tend to bend and they tend to twist. They tend not to break, though. They tend to just sort of like stretch and stuff. And because that happens, we can see basically how molecules are interacting with heat. And this FLIR, forward-looking infrared, is what you're looking at when you start to see those cool infrared images. And so I'm going to show you guys one. Let me stop my share for a second and make sure you guys can see this. So if you're taking a look, it's kind of neat. So I have a forward-looking infrared camera here. It's from the good people at Snap-on Diagnostics. And if I put this in front of the camera here, you guys can see that this is me in the near infrared. You might see that like all around my head, this is where a lot of heat is escaping my body, but not a lot here in my nose. So my nose is considerably cooler than the rest of my head. And if I just sort of like press against my face there, I might see, it's not showing up all that great. But if I have my coffee here, my coffee is really hot compared to the rest of it. So here's my cup of coffee, right? And there it is in the infrared. See what that does to my face, like just really increases the heat on my face. Kind of neat. Turn that off. Go back to screen share. Isn't that cool? I think it's cool. Okay, so infrared becomes really important in organic chemistry, where we look at how that's one of the ways that we can actually classify molecules. Now, what we're seeing here, the inside of your body is like 98 degrees. And if you're standing in a sufficiently cold place and you have forward-looking infrared cameras around, which we're seeing more and more of because of how we can help maybe detect a virus, this is something you might see. So like a person letting out a little bit of gas on a cold day. There you go. Near infrared is a really neat one. And you see there's a lot of cameras that are doing this. A hazy day in San Francisco Bay would look like this to your eyes. So if you're on a boat and you're trying to navigate this, this would be a challenge. Hard to really know what's out there. A near infrared camera would look at the same thing, and because it's looking at a different part of the spectrum, it would be able to see through things like haze, like water. So water is transparent in the near infrared. And as a result, the haze that's here around the bay just basically doesn't appear to this camera. So it gives you a much clearer view. Other things are also kind of invisible in the near infrared. That includes hair. You can see through hair in the near infrared. So if you're looking at something like looking at a person with this, you can kind of see through to their scalp, should you want to do that. I've been doing it for a while. Other infrared camera images. Here's a cat who is clearly evil, thinking evil thoughts, but you can see a lot of heat escaping from its eyes, but not a lot from the rest of its body because it's insulated with hair. Here's someone holding an evil scorpion for some terrible reason. Scorpions are cold-blooded. So if they were to put this scorpion down and run for their lives, you would see like there's a red spot right there in the tail where they were holding it. An idiot. This is an evil child, and you can see that the hair on the child's head is kind of insulating, so we don't see as much heat escaping there. We don't see a lot of blood going through ears either, and so this is one of those things you watch out for in really cold weather. If you're out in really cold weather, you want to be wearing a hat, one, to kind of keep any heat that's on your head near your head, and then also covering your ears because you don't get a lot of blood through your ears. Yet this is still precious skin and stuff, so you want to take care of that. And this is what's called a no IR version of the camera. So this camera right here, what it's showing is basically someone who would look in the darkness of night. You may not see this person, but if they were radiated with infrared light and looked at it with an infrared camera, you'd be able to see that this person's, you know, climbing a fence. Probably shouldn't be doing that. And so this is what a lot of security cameras end up looking at. So it's kind of, again, a really neat use of the technology. Okay, microwave radiation. This is on the order of 10 to the minus 2 meters, and so now we're talking about things that are centimeters long. And microwave radiation, they cause entire molecules to vibrate. One would be like water. So water will vibrate back and forth really fast, and that's what ends up happening in the microwave ovens that we have in our houses. Microwave ovens, for as much flack as they can possibly get, have really made it possible for a lot of people to heat food without using a whole lot of energy. So I have a lot of respect for microwave ovens. We used to say we'll go nuke something. That was the way we talk about our microwave ovens. And the frequency, again, as this gets larger, this keeps on getting smaller, which means we're dealing with a lot less energy. So X-ray radiation is enough to blow molecules apart, even blow atoms apart in some cases. Microwave radiation really only just kind of makes them shake ever so slightly. Radio radiation, these are waves that are on the order of like 1 meter long, so they're really big waves. And these are what we use for communication because the energy to make them is so low. We're talking about 3 times 10 to the 8th hertz here. So this is kind of an easy band for us to get at. And this is a vibration of very specific molecules that are in our air. And so radio waves and then hydrogen waves sort of like out into space. They're very low energy, very easy to produce. So any communication that you end up doing with cell phones work on a radio frequency. And that's because if it took something like X-rays to communicate, that's the equivalent of taking 2 planets and banging them together to, you know, communicate a signal. Whereas this, all I got to do is use a tiny amount of energy, and it's relatively easy to get a signal. The FM band on a terrestrial radio is in the megahertz range. So when you're changing stations on a radio, you're actually tuning to a different frequency, and that's anywhere from 87.9 to 107.9. The AM band is 540 to 1600 kilohertz. Chances are your parents are in the generation that saw popular radio change from AM to FM in their lifetime. I kind of came in when FM was mostly the established one and AM was kind of going away. Now, many are surprised that it still exists. Cell phones tend to operate at 1900 megahertz and 800 megahertz. And allocation of this band is actually a very important thing. So if you are an engineer that is looking to go into spectrum management, it's a very important thing. There's only so much bandwidth to go around. Yet we are very reliant on this for communication. And so there are ways that you can interact with this. This is a Raspberry Pi setup that I built that is scanning radio bands, so it tells me where various signals are depending on where I am. And this is what's called a spot finder. And so there's a lot of these GPS sort of finders that you can use that tell you where you are. So if you're a hiker or something, and this is something that you want to use to communicate where you are in the world to someone who might need to find you, this is an easy thing to do. We use this in some of the ballooning programs I worked in. And then there's a local company called SoftWorks that does a lot of work in the radio spectrum. Now, let me pause here. Are there any questions on any of the things that we just went over? The main things you want to keep in mind, mathematically at least, are lambda times nu equals c. Conceptually, you want to know what is in what's at various portions of the electromagnetic spectrum. So if I said, what has a higher wavelength, visible light or microwave, the wavelength is larger for microwave than it is for visible light. So you'd want to know those sorts of things. And then we're going to get to the energy calculation for this in just a minute. Any questions? Okay. There is, if one of you is not muted, which is fine as long as things stay quiet. But just so you know, one of you is not muted.
Oh, that's me. I'm so sorry.
That's okay. All right, so photoelectric effect. So your book goes into the photoelectric effect. I'm going to go into it just a little bit. If I have some chamber here that is evacuated and I shine light on it, what it'll do is it'll eject an electron. And then that electron will show up in, on a current meter. And this was known for a long time. People have been seeing this. When I shine light on metal surfaces, I end up getting some current coming out of that, and that was kind of neat. Why that happened and exactly how that happened was a mystery for a long time, going into the early 20th century. So one of the things that was observed about this is that if I just shined light on it, generic white light, and I started tuning the frequency of that light, at low frequencies, nothing would be happening. And then all of a sudden at one frequency, there's a jump. And I'm giving off a whole lot of this stuff. And then as I continue to increase the frequency, it stays at that level, which is weird. Why is this so attuned? And also, if I change the intensity of light, so the frequency doesn't change, but if it's more intense light, like brighter, that means I'm giving off energy. These particles are coming off, but they have more energy when they come off. And the particles are coming off here and they have less energy when they come off. So these are two things that were puzzling scientists for a long time. And Einstein was the person to give us some ideas about this based on work done by Max Planck back in the early 1900s. So just at the turn into the 20th century. He developed what's called Planck's constant. It was featured in Stranger Things, season 3. And it was also really important in the way they redefined the kilogram, which is another thing entirely. So here we go. We've got Planck's constant here, and it's an incredibly small number. Look at that, 10 to the minus 34 joules times seconds. What is Planck's constant? Well, it's a number that we can use to associate the energy of a wave and its frequency. So the energy of wave is directly proportional to the frequency, and the proportionality constant is Planck's constant. Okay, so E equals h times nu. So this frequency is also in the wavelength equation, and so lambda times nu equals c. So I can solve this for nu, plug it in, and now I have a new equation. The energy of a wave is equal to h times c over wavelength. So there are two equations here that'll do the same work for us. If I only know the wavelength, that will get me the energy. And these two are constants. H is Planck's constant, c is speed of light. So if I have a large wavelength, it means I've got a low energy. The denominator is big, so energy here is small. If I have a small wavelength, like X-rays, that means that this number here is small, my denominator is small, so my fraction is big. Okay, so energy ends up going up or down with frequency. What Planck's constant really means is that energy is distributed in tiny packets, and the smallest of the packets that we can get is equal to like 1 of Planck's constants. So most people thought, and there's a video I did on this that's on our webpage, on my courses page, that energy was sort of a continuous thing, and it's not. Energy is discrete, or it's quantized. And what it means when energy is quantized is it's given off in tiny packets. Now, the little analogy I use for something that's quantized is donuts. I love donuts. So if someone says, Mike, do you want to split a donut? I'm like, no, I want the whole donut. Donuts are quantized. Can't have a quarter of a donut. You have a whole donut. Same thing with energy packets. If something is giving off energy, it's doing it in packets, numbers of packets, all right, never fractions of a packet. So a question that might come up about this, this is one that I took out of our text. Determine the number of photons in a laser pulse of 345 nanometers, and that laser has an energy of 5.85 millijoules. So how many photons is that? Photons are like these little bits of light. So how many photons is that? All right, well, the photon wavelength itself is 345 nanometers, which is 345 times 10 to the minus 9 meters. The energy of a single photon would just end up being, E equals hc over lambda, just kind of what this is. You can figure that out pretty easily. So E equals h times c over lambda, which is that, 5.76 times 10 to the minus 19 joules. So now I know the energy of just a single photon that has this wavelength. But let's say it's coming from a laser pulse that has that amount of energy, 5.85 millijoules. All right, so the number of photons is the number, the energy of the pulse and the energy per photon. So if I take the total energy from the pulse divided by the energy per photon, I get the number of photons, 1.02 times 10 to the 16. Should be a large number. A lot of photons are contributing to that. If I were to turn up this number right here, make it a higher energy, I would be getting more photons out. That's the basic premise behind a movie called Real Genius, which if you have not seen, you should see. Now, that brings us to like the actual biggest mystery that existed in the turn of century, 20th century, going into the 20th century for this, and that is a hydrogen emission spectrum. So the hydrogen emission spectrum is this idea that if I have a tube that's got a bunch of hydrogen in it, and I pass a huge amount of energy through it, and then it glows. It's going to glow some weird color. So it gives off a certain amount of light, so I run that through a slit to make it nice and straight. I run that slit through a prism to separate it out into what it's made of. And instead of getting every color of light, which is what I would expect, I get very specific colors of light. I get a few different lines, and that doesn't make sense. How is it if I'm giving this a whole bunch of noisy electricity, which is every possible wavelength, that it's only giving me specific wavelengths back? I don't understand why. And this was the mystery. The early 1900s, this was the mystery. So the emission spectrum that we were seeing from something like hydrogen would look a little like this. Now, this I actually believe is helium. This is what's being emitted by that source. And so if something is absorbing that light, these wavelengths are missing. So these are always complementary things. Sometimes you'll see an emission spectrum, sometimes you'll see an absorption spectrum. We usually use absorption spectrum in our characterization of different molecules. So this required a new model of the atom. So Bohr, Niels Bohr, came up with this model. His model is quite simple. It looks like this. Here's a nucleus in the center. And then just in these series of half circles, these are places where there is an orbit that is big enough to accommodate an electron. And when an electron moves from an outer orbit to an inner orbit, it gives off some energy. Going from this third orbit to the second orbit corresponds to the amount of energy that would go with this red wavelength. It corresponds with it exactly. And one that goes from this fourth orbit to the second orbit corresponds exactly with the amount of energy that would go off with this 486. And same thing here with this violet, from the fifth energy level to the second energy level. So Bohr's model of the atom worked like this. All right, a nucleus is in the center of the atom. Electrons are somewhere on the outside in these orbits. It can be in this orbit or it can be in that orbit, but it can't be in between those two orbits. So an electron moves from the fourth energy level to the second energy level. It's not going through the third energy level to get to it. It simply disappears from here and reappears here because the electron cannot be anywhere but in a loud orbit. And these orbits are based on like classical physics. You basically model like it's a solar system. And Bohr's model worked. It was amazing. So he postulated that electrons existed outside of the nucleus of the atom and that there were orbits at allowed distances, and he used another scientist named Rydberg. He used that guy's equations to figure out what those distances must be. And then he used classical mechanics to model how electrons orbit the nucleus, and basically like planets orbiting the sun. So he used those kinds of mechanics to figure these things out. And when an electron absorbed some energy, it disappeared from an inner orbit and reappeared in an outer orbit. So absorbing energy meant that an electron went from close to the nucleus to far away. And that's absorption. Emitting energy meant that it came from far away, closer to the nucleus. And then difference meant that energy was being given off. And so what does this mean for the spectrum? It means that when we saw that hydrogen emission spectrum, hydrogen was only absorbing the wavelengths that would allow electrons to go from one orbit out and then back again. That's why it can't absorb all wavelengths. It would only absorb ones that it had room for. So this explained the hydrogen spectrum. And for this, he got a Nobel Prize in 1922. It is very important to remember, we knew that there were atoms a long time before we knew what they looked like. We knew that had a nucleus, thanks to Ernest Rutherford, but that wasn't until like the middle 1800s. So, or in the middle to late 1800s. And so explaining this Nobel Prize and saying, I know where the electrons are and I know how they move, this was a big deal. This was Bohr's model. But there were some problems with that model. So here's the spectrum, the emission spectrum from oxygen. Here it is from neon. My goodness, there's a lot of lines in oxygen and neon. Well, Bohr's model was deterministic. And what that meant was that he was using classical mechanics. And being deterministic means that if I know where I am now, it will determine where I'm going to be next. Everything going like on an arc, or things along those lines. And it relied on stationary states. These electrons are in these stationary orbits. But most importantly, his model would never predict the spectrum for any atom other than hydrogen. It only worked on hydrogen. When he tried to apply it to helium, it didn't work. There were some fudge factors that had to go in. When he tried to use lithium, it wouldn't work. However, if the helium was ionized, there's only one electron, then it worked. And if there was only one electron in hydrogen, which there is, it worked. So the model would not work on multi-electron atoms. It only worked on single electron atoms. So this model is fundamentally flawed. Bohr's model, while a good and important step forward, is not the appropriate or correct model of the electron, of the atom. It's fundamentally flawed. So now we're making progress to what we're going to call the quantum mechanical model of the atom. And this has a couple of things that go along with it, one of which is what's known as the de Broglie-Waite relationship. This is something we'll do some math with. It's in your homework. You'll see it here. But it's this idea that the wavelength of something is equal to h over m times v. This is something I would usually in class derive. There really isn't the right venue for this now. So take it on faith that the wavelength of light is equal to h, this constant, over the mass of the particle times the speed of that particle. This v is the speed, not its frequency, but its speed. There's something really weird happening with this. All objects with mass have some kind of wavelength. And all wavelengths have some kind of mass. This is the first equation that put two of those things in the same relationship. I would normally not look at something like my calculator, which I know has mass, and say, what is your wavelength, calculator? This doesn't behave like a wave. Nor would I look at the light overhead and say, I wonder what that light weighs. But according to this equation, there is a mass associated with it because wavelength and light are in the same equation. So the de Broglie wavelength is one thing. And let's actually go forward with the math on that for a second. So we can actually determine the de Broglie wavelength of things. So what's the de Broglie wavelength of an electron whose mass is 9.11 times 10 to the minus 31 kilograms, traveling near the speed of light, 2.65 times 10 to the 6 meters per second? Well, this is the equation that I used to solve this. So I just plug in the things that I need to plug in, and my wavelength comes out to be 2.74 times 10 to the minus 10, somewhere in the X-ray range. That's a meaningful wavelength. That means that for an electron, I have to pay attention to how it's behaving like a wave while I have to pay attention to its mass. One other thing I'd like to point out is that a joule is a kilogram times meters per second squared. And so, again, take it on faith that with the units that are on this side of the equation, we do end up with units of meters on this side of the equation. So here, I've got joules, kilograms, and meters per second. On this end, we just end up with meters. And that's because of this relationship. Now, a baseball will be starting again soon. Yeah, Cubs. A baseball weighs 145 grams. That's in the rules. And let's say it's traveling really fast, and fastball, 97.5 miles per hour. What's that wavelength? So I need to know, instead of miles per hour, I can't really work with that. Meters per second is what I need. 43.58, we just, do some calculations or run some Google and figure that out. Plugging in again, h over mass times velocity. I get something that shows 1.05 times 10 to the minus 34. That is incredibly small. That is smaller than gamma waves. So something like a baseball, which is very heavy, 145 grams, moving very slow, a mere 43 meters per second, will have a wavelength that I can probably ignore. There's no real wavelength worth talking about there. Let me go back to this. So now, so there's wavelengths there. The other thing we need to pay attention to is what's called Heisenberg's uncertainty principle. So Werner Heisenberg is a person worth noting in all of this. Depending on the biographies that you read, and this is something I'd recommend everybody do, because the personalities in science at this point are so interesting, and they were involved with the war efforts in their respective countries. Heisenberg was German. This is a really interesting time frame. So de Broglie was a radio person. He kind of worked with radio waves. Heisenberg was German, and Einstein, German. He came to the U.S. A lot of really cool things going on with all the different personalities and names you've heard of. They were all colleagues. What he stated is that the product of two things, the uncertainty in position, x, times mass and the uncertainty in velocity or vector of where you're going, is greater than or equal to some number that is not zero. So h over 4 pi, which means that there's a limit to the certainty of any measurement. I think you know this. If you're using your phone to navigate and you're on a city street and you're walking around, one, I hope you're looking where you're going, but two, you should be able to notice that, like, it says I'm right here, but that probably means I'm within, 10 feet in this direction, 10 feet in that direction. It's only so precise. Well, according to Heisenberg, there is a limit to that precision. So if my precision in x is absolute, meaning that my uncertainty, this delta x, plus or minus wherever I should be, is 0, then my uncertainty in velocity needs to be infinite. Because if this is 0, then I must multiply by infinity to get any number other than 0. These are imaginary things, of course. This is not a real number, it's a concept. But the idea is that the more I know about my position, the less I know about my direction and velocity. Conversely, if I know this really well, I know where I'm going, I have no idea where I am. So there's a limit to how much I can know both of these things at the same time. I will always have some amount of uncertainty in both of these simultaneously. And because we have to deal with uncertainty, we need to think of a way to deal with how electrons are moving around. Which means that the electrons, they cannot be treated deterministically. So how Bohr decided to treat the electrons, their past determines their future. We can't treat electrons that way. Where they are now has nothing to do with where they'll be next. So move back through this stuff. So Erwin Schrödinger is, Schrödinger, the guy who's famous for Schrödinger's cat, a nice analogy for how you think about these things. He created a way to describe the relationship between theories and observations. And he literally made this up. He was on a ski vacation with someone he was not married to, something he apparently did a lot. But he came up with this equation, which is psi h equals psi e. And you're like, well, cancel out the si's, h equals e. Donezo. No, that's not how it works. This is a wave equation, and this is a series of instructions for that wave equation called the Hamiltonian operator, another wave equation, and the energies associated with that wave equation. So it's actually a very complex one, but it's symbolically represented like this. You can't make this up from first principles. He literally made it up. First principles means you can go back to F equals ma and derive this from natural law. You can't do that with this. It just so happens that it works. When you try to model electrons using Schrödinger's equations, you come up with stuff that actually works, that is observed. So when this function is squared, it determines what's called a probability map. And that probability map has the name of an orbital. So instead of dealing with orbits, like, what's his name? Bohr used to deal with, we're dealing with orbitals, a 3D volume of space where there is a 98% chance of finding an electron or better. So in a classical trajectory, where this is given some sort of velocity vector, we know how it's going to go up and then come back down. An electron that starts here, 1 second later, could be in any one of these positions. And that position that it's in has nothing to do with the position that it was in. So this is a classical way of dealing with things, and this is a quantum way of dealing with things, as a probability, as a distribution. And it's funny, Einstein was a guy who used to think about these things a lot, and one of the things he thought about was, okay, we know what a half-life is, right? You know, how long it takes for something to decay down to half of what it started with. So we know what that works like when you have like 100 atoms or something. But what is the half-life of just one atom? It doesn't wait a certain amount of time and then just sort of like pops out of existence. It goes when it goes. So things like half-lives are, in a sense, a probability for a big group of things. Or that probability breaks down, we're looking at just one thing. So when you solve Schrodinger's wave equation, you would do this in upper level classes. We're not doing that in this class. You get 4 numbers. Here's one of them. The principal quantum number. That is the number n. That tells us about the size and energy of this, and it can have integer values, 1, 2, 3, and so on. So what that tells us about is how big the orbital is and how much energy it has. So an n equals 1 orbital would, be this big, and n equals 2 would be bigger, and n equals 3 is bigger, and so on. So that is the numbers that it can have. N can be 1, 2, 3, and so on. Another number you get out of this is called L. It's a cursive L. It's the angular momentum quantum number, also known as I think it's the azimuthal quantum number. And this tells us about the shape of the orbital. So when n is equal to 1, L can have values as high as n minus 1. So it can have values of 0, 1, 2, 3, and so on, all the way up to n minus 1. So if n has a value of 1, the only value L can have is 0. If n has a value of 2, the values L can have are either 0 or 1. And so here, when n has a value of 2, L has a value of 0, and that describes this kind of shape. When n has a value of 3 and L has a value of 0, that describes the same shape, but it's a little bit bigger. These are what we call the S-shaped orbitals, and we'll get to shapes of orbitals and names in a minute. The last one that we're allowed is, sorry, the third one. The fourth one is a pair of numbers that we'll get into next time we talk, is the magnetic quantum number. And that tells us about the orientation of the orbital, so how it's arranged in space. So it can have values of negative L up to 0 up to positive L. So whatever the value of L is, it can be on the negative side, and then integer values up to 0, integer values again up to positive L. So some allowed sets. So if n is equal to 1, the only value L can have is 0. The only value m sub L can have is 0. So each orbital can hold up to a total of 2 electrons. And here's what a 1s orbital would look like. An S-shaped orbital, spherical, at the first energy level. So there are some allowed sets here. So if n is equal to 2, L can be equal to 1. M sub L can be negative 1, or negative L to 0 up to positive L, so negative 1, 0, or 1. And that describes these orbitals right here. These P-shaped orbitals. There are 1, 2, 3 ways to arrange it in space. So along the X, along the Y, along the Z. So there are 3 electrons there, or 3 ways to arrange these orbitals. And if n is equal to 2 and L is equal to 0, then we're talking about this S-shaped orbital here. There's only one possible value for m sub L. So when L is equal to 1, this describes what's called a P-shaped orbital. That's what these are, these dumbbell kind of things. And when m sub L is equal to these numbers, these are the different ways that we can orient it. Moving up in the world, when n is equal to 3 or more, L can be equal to 2, which means that we can have negative 2, negative 1, 0, 1, and 2, different ways of organizing these. If n is equal to 3, then L can be equal to 0, and m sub L can be equal to 0 as well. So at the third energy level, there's different ways that we can orient these things. So when L is equal to 2, this describes what's known as a D-shaped orbital. And there are 5 different ways that we can have this. 1, 2, 3, 4, 5. So there are 5 D-shaped orbitals. Each can hold 2 electrons. Moving on to n equals 4. When n equals 4, if L is equal to 0, m sub L can be equal to 0. If L is equal to 3, m sub L can be equal to negative L all the way up to positive L, including 0. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. There are 7 ways that we can represent that, and there are 7 what's called F-shaped orbitals. Lobes all over the place. Okay, so when L is equal to 3, this describes an orbital that we call an F-shaped orbital. There are 7 of them, each can hold 2 electrons, and so there are 14 electrons that can be held in this entire group. That kind of takes us through the whole of that chapter. Screen sharing here is done. So it's a little longer than I would typically go, but there's no other real good breakpoint. What we're going to see next is how electrons will start to populate those orbitals and what that tells us about how those electrons behave. So periodicity is what we're getting into next. So the next chapter that we're working with here is the 9th chapter. Most of your homework ends up coming out of the 8th chapter, but I'll give you guys some things to do in the 9th chapter as well. But in the 9th chapter is when we get into electron configuration. And so that's when we see that 1s2, 2s2 kind of stuff. Okay. I've put up, I think there are 3 videos on the class website that complement the things that we did here, spent a little more time on some of the things that we talked about. The third of those videos is something that we won't be seeing until, you aren't going to cover any content until later on. I want to share my screen for one more thing here. I think this is the screen that I want. Yep, it is. So I mentioned the fact that all of this happened in sort of contemporary history. So this is a play called Copenhagen. That's Daniel Craig. You might know him as James Bond. Anyway, this is a movie. It's actually a play that this movie is based on, and it's the conversations with Werner Heisenberg and Niels Bohr. And Heisenberg is a student and kind of a colleague of Bohr's until they find themselves on opposite sides of the war. Bohr is Danish. He is German, and he's asking questions that kind of relate to things that he interprets as part of the bomb. So these 2 people stop talking to each other, and this play is about their breaking communication. If you're at all interested in this side of history, what was going on with scientists during the Second World War and how that would come to a close and how America would get so many of the scientists basically to provide safety and then also to sort of like use them in our own manufacture of the bomb, it is absolutely fascinating. And stories like Copenhagen go a long way. So it's something that I'd strongly recommend to take a look at. I saw this play performed once. I've never seen the movie. I have a hard time finding it, but I'm sure it's out there. So that is it. Al, I
had one question about wavelengths.
Questions, concerns, violent objections, anything like that?
Can you hear me?
I can.
I had a question about wavelengths. You said that wavelengths have mass, and what kind of mass are wavelengths made out of? I thought it was just electrons, but can they be made out of anything else?
Wavelengths aren't necessarily electrons that are moving.
Okay.
Wavelength, anything that has a wavelength has a mass associated with it. So are you familiar with the idea of like the solar sail?
No, but I'll look it up.
Okay, so in certain designs of like satellites and things that are going to go between planets, what they do is they sort of put up this giant sail out in space, and it turns out that because light from the sun is just being given off in all directions with a lot of energy, the mass that's associated with that light will impact the sail and push it in a certain direction, and you'll keep on getting that push.
Oh,
so
wow.
Taking a more like contemporary one, like if you ever look at the Marvel movies and Iron Man, like when he puts his arm out and shoots light out of there, he kind of recoils. And it's a movie thing, so I don't want to put too much faith in it, but that recoil is accurate because it's basically mass leaving, or a certain amount of mass is being forced in a certain direction. So wavelengths do have a mass associated with them, although it is super, super small. So if you decide to weigh yourself in the dark, and again in the light, you will never notice the difference.
So the mass of a wavelength is actually the air that it's moving through?
No, the mass of air is the mass of air.
Okay.
It's a wavelength. It's an association between mass and wavelength. And the more important thing to think about is the wavelength of mass. And so like everything vibrates to some extent.
Right.
And something like a baseball vibrates really, really little. Something like an electron vibrates an awful lot. So the vibration or its wavelength is really important when you're an electron, really unimportant when you're a baseball.
That makes sense now, because the baseball question totally confused me. I was like, how does a baseball have a wavelength? But if everything vibrates, everything has a wavelength.
Correct. Everything vibrates. Baseball does have a wavelength. It's just that it's so small, 10 to the minus 34. We can effectively ignore it. Although 10 to the minus 34 corresponds to a lot of energy. If you were hit with a high energy electron, you wouldn't notice. Hit with a high energy baseball, you'd totally notice.
Yeah, I see what you mean about this. It's more conceptual.
Yeah.
It's a class.
Yeah. Yeah, you can do the math with it, and the math's correct. But this part of the class is a lot more conceptual. Great question, thank you. Others? This is a fun part of the class. I get really excited about this content. Okay, I'm going to end it here. The recording's gonna be kind of long.